recording it so you can look at it later. And start recording now. Okay, so for the benefit of a slightly late recording, the idea is that we're going to use a simple pendulum to try and determine quantify the value for acceleration due to gravity, which we know through previous experience that it's about 9.81, but we're going to determine our local value where we're currently staying at the moment, and that might be to see if we can get a number which is near enough that figure at 9.81 newtons per kilogram. And the link that's in the chat box will take you to a mathematical relationship between acceleration due to gravity, the time periods for a pendulum, and the length of a pendulum. Okay, so got any ideas how we might use that knowledge to determine G? Put it in the chat box, or if you prefer to just talk, if you just put your hand up, I will unmute you. And you can make a suggestion. Okay. Okay, so what you should be thinking then is what is the mathematical relationship then between time periods and the length of the pendulum? And you should have discovered this relationship here. So we have T time period, 2 times pi, of the square root of L over G. And G is our acceleration due to gravity, L is our length, and T is our time period. But what do we mean by the time period of a pendulum? Just going to come out of sharing again so you can have a look at this. Time period for a pendulum is the time for one single oscillation. Sharing. So that is the time for the pendulum to swing both one way and back again. So one oscillation is there and back. Now, this experiment only works if you use very small angles, so angles less than 15 degrees. So you want to just displace your pendulum by about 10 degrees or so, and let it swing. And you're going to have to establish the time for that. So one way in which we make experiments more reliable is by having repeated and average values. So rather than just trying to quickly time one swing, a better approach for me to do that is to let it swing there and back maybe 10 times. And after 10 times, I simply divide that amount of time by 10, and that would give me my time period for one single swing. And that's just a way of improving the accuracy of our results. It reduces what we call the percentage uncertainty in our measurements. Every measurement we make will be certain to a certain value, but will have some uncertainty based on the precision of the instruments that we're using and how we're recording those values. So to improve that, we record maybe over 10 oscillations and take the average over that time. If you don't have anything that you can use at home to set up a simple pendulum, then there is a resource that was also emailed out to you, but again, I'm just going to put the link into the chat box, because you have the opportunity then of using the simulation in order to try and get the acceleration of gravity on the moon or on Jupiter or different planets. So you can use that information to the same relationship in order to try and establish what value G is in those other objects. or country models. Okay, well, I'm going to give you just 5 minutes to have a go at that, and we'll see if we can get values that are of the right order of magnitude. 9.81 for the Earth, or we'll find out what we get if you do a different planetary objects. Any questions? Either put them in the chat or again, put your hands up and I'll unmute you. The link to the simulation has just appeared in the chat box. Okay, we're hoping you can see the presentation, the practical challenge. I think if you click on the link, so that link's also in the chat there, that will take you to a simulation. What we're trying to do is use this equation, the time period equal to 2 pi of the square root of the length of the pendulum over gravitational acceleration. We're trying to use that in order to get a value for G. From the simulation, if you go to the introductory tab, click on the University of Colorado PhET simulation, and then you do the Pendulum Lab with the introduction, then you can select a planet or a moon to be your host planet, use a stopwatch facility and try and time a number of oscillations to get the value of the time period. Once you've got the time period, you can substitute the values of L into this equation to try and determine the value for G. You can work out the value of G on a different planet, or if you've got this equipment set up, if you've got somewhere where you can construct a simple pendulum just out of any old piece of string and bunch of keys or anything with weight to keep the string taut, then you can actually do it practically yourself in your home. And once you've got your values of your time periods, or your capital T's here, you need to think, well, how can I rearrange this equation so I can make G the subject? The easiest thing to do here is to square everything. T squared equals 4 pi squared L over G. And if you're making G the subject, change this. Four pi squared times the length, all divided by the time period squared. So you can take your value for your length of your pendulum, measure from the top of the pendulum to the middle of the mass. So this one here is about 30 centimeters. You put that in SI units, 30 centimeters becomes 0.3. My time period, which I've calculated by averaging over the number of oscillations, and plug that in there. And if I do that, I should hopefully come out with a value of G being more or less about 10. I'm not worried about it being 9.81 specifically here. It's more or less about 10. It could be 8, it could be 11. Around the 10 value, then I know that generally my experiment has gone as planned, and I can be confident that I've got a valid result for the local measurement of acceleration due to gravity. What you will learn in September is how we can then apply different mathematical tools to say exactly how confident, what is our percentage uncertainty in our investigation. Can we increase the precision of our investigation? Well done, Fernanda. 8.4, 8.5, we'd round it up to 2 figs. That's pretty much spot on when it comes to physics. You're certainly within the correct ballpark. Do you have any advance in 8.499? Hello now. I'll just give you a couple more minutes to finish up off any calculations or any last bit of investigation. Then we'll move on, because you can do this in your own time as well if you want to try and put your physics practice, your physics knowledge in practice, to see how we can use just everyday objects to form what is essentially a universal constant, and use that value in our calculations. I think 8.499 is going to take the prize then for being the most accurate value that we've got. We'll push on because we've only got so minutes left, and there's a few other things I want to get through. Then I have to introduce the summer task, and going to focus on a couple of other aspects of thinking like a physicist as well. I mentioned earlier that sometimes our initial concepts have to be challenged, and that's what physics does. It pushes you to think in different ways and to apply mathematical ideas into everyday common experiences. Before I do that, I'm actually going to flick to the last slide, just so I can tell you about the summer task at this point, so I don't run out of time at the end. So we ask all students who are considering starting physics in September to prepare some work beforehand. So you're going to use this time that you've got this long summer holiday to start preparing yourself for A-level study. And there's two things that we want you to do. One of these is a knowledge-based task. So it's looking at your prior knowledge that you already have from GCSE and elsewhere about physics, and to have a go at answering some challenges, some questions in a workbook that would be emailed out to you, or you can download it. If you're a Shenley Brook End student, you might already have access to GCSE Pod already, and you can get the additional resources from there. So it's just kind of, a few physics questions, stimulating your mind, getting you to recall what you already know. The second part I find a bit more entertaining, and it's a research and presentation task. Part of your assessment in physics is in practical skill, including research and presentation, which you'll need to be able to master by the end of the course for the practical endorsement in sciences. To get you kind of prepared for that, we're going to ask you to think about something that you're interested in. That could be sports, it could be a hobby, it could be travel, it could be something that's already physics oriented, space and astronomy, medical physics, physics in hospitals, that kind of thing. And around that concept, we wanted to think of physics in bold and to put together a 10-minute presentation, probably through a PowerPoint slide presentation. Doesn't have to be PowerPoint. You can use any presentation you fancy. But the idea is that you'll be presenting along to the class within the first couple of weeks that we start the course with. Again, previously we've had black holes, we've had physics of mountain climbing, we've had physics of Formula One, physics of the weather. People are interested in weird stuff. There's no kind of limit on what you can apply this to. Feel free to be creative with that and think how you might wrap that up in a 10-minute presentation to the rest of the class. So that will be in the first couple of weeks of starting the course, and then the knowledge-based task. We'll give you a little bit of extra time because we haven't had the opportunity to do it over the summer holidays. But I think within the first 4 or 5 weeks back, we'll be asking you to submit that knowledge-based task as well. Okay, so that's the summer transition task. That is all available from Teams and from where the rest of your transition resources will also be available. Okay, I'm going to go back now. I'm going to go to this slide, which is just about what is physics. So you've all signed up for physics, you've had a bit of experience with it at GCSE. How is it different to other subjects? And what is it at its core? And one of the best explanations, I think, that I've ever come across with physics is that it examines the interplay of matter and energy in the universe. It sees how those two things behave and how we can make predictions and solve challenges regarding the fundamental interplay of those two fundamental concepts. And the next few slides are going to contain a number of questions. And these questions are relatively simple questions, but the answers are a little bit more complex. What I want you to do is on each of these, put into the chat box or put your hand up and feel free to talk, and I'll unmute you. What are the underlying principles that we need to know in order to answer these questions? So we'll go through the first one together. Will an ice cube melt faster or slower if it is immersed in a glass of water or left alone on a table? The question is relatively straightforward. What will happen? So what do we need to consider when addressing this question? What are the underlying principles that it depends upon? Okay, good. So we've got some ideas coming up on the chat box. So heat conduction of water versus air. So absolutely, how is that heat going to leave the ice? Now, heat is generally named for thermal energy. We need energy to be transmitted. So we could have conduction into the air, the convection in the air, conduction directly through the table surface. That's something we need to know. Faster left alone is a suggestion. Who agrees? Who thinks it's going to be faster if it's left alone on the table? It's actually a question without a necessary answer. There's so many factors that we need to consider. What is the temperature of the surrounding air? What is the surface area in contact with the air? What is the volume of water? What is the temperature of the water? All of those factors have a effect on this situation. And when we conduct scientific investigations, we always have to go back to the idea of, well, I've got an independent variable and a dependent variable. I need to devise an experiment in which I'm just varying two things. I'm looking at the effect of one thing on another. And everything else needs to be constant within that investigation. So the idea of conducting scientific investigations always has to start with the idea that you've got independent and dependent variables, and everything else needs to remain the same. There's lots of variables at play here. As we said, surface area, conductivity, thermal gradient, which is the difference in temperature between the ice, the initial temperature of the ice, the initial temperature of the surroundings. All of those will have an effect on whether or not the water, the ice cube left alone will melt faster than the ice cube immersed in a liquid. So we can't answer that directly. The second question I'm going to pose has a definite answer. So I want you to make a decision when you think of the problem, and you're either going to answer for situation A or situation B. The book is standing on its ends. You have the choice of two objects of equal mass to throw. One is a highly elastic rubber ball, going to bounce off of the book. The other is a wad of extremely sticky tack that when you throw it at the book is going to stick to it. It's going to adhere to the book. Which of those two objects is the most likely to knock the book over? Assuming we hit the book in the same position, somewhere near the top, is it A, the highly elastic rubber ball, which is the most likely, or B, the ultra sticky tack? Both the same mass. So the A or B or ball or the tack. Okay, I'm good to see we've got some conflicting answers here. And this is what it's all about. It's about having three concepts that we're happy to challenge. No, there's no right or wrong answer in this case at the moment. It's just your concepts. Whether the concept was right or wrong will take a little bit of explanation. We'll look at that in a minute. Let's have some more answers. Is it A, the rubber ball, or B, the ultra sticky tack? Be brave. Put your concept down. There's nothing wrong with having a concept, whether it's right or wrong. What we need to discover is how do we analyze those? How do we apply mathematical tools to determine what is the correct answer? Okay, so a few more answers. A few of you heads in your bets. You're not willing to commit. Is it the ultra sticky or is it the bouncy ball? Good. We've got some explanations coming in here as well. Perfect. You're not just stating, but you're also giving some explanation. I apologise, you can't hear me. Does everyone else have the same issue? Is the sound a little bit muffled? I'm not sure what happened. That unfortunately, there's no microphone attached. I've just got to use the computer audio. So if you choose A or B, miss slides. Okay, well, I'll put you out of your misery on this one. The correct answer, as many of you determined correctly, is the elastic ball. So the elastic ball, when it hits the book, is going to bounce backwards. Now, if we remember our Newtonian physics, our laws of motion, then we should remember that the force exerted on an object is equal to the rate of change of its momentum. The stick, the ultra sticky tack is going to hit the ball, hit the book, and then it's going to slow to zero. So the change in momentum there is its mass times velocity in the initial minus zero because it's come to a standstill when it's stuck. However, the bouncy ball is going to be moving first in one direction, and as we know, velocity is a vector, it's going to bounce backwards. So the velocity becomes negative, and we have a greater change in momentum for the elastic ball, giving us a much greater likelihood that throwing the bouncy ball at the book will knock it over, whereas the ultra sticky tack is less likely to do so. Okay, I'm going to do one more physics funk. If a child is seated in the rear passenger of a car, traveling at constant velocity, the child is holding a helium balloon, what is going to happen to that balloon when the driver applies the brakes, bringing the car, cause the car to decelerate? Okay, so think of the answer to this and yes. Helium balloon will be pushed to the back of the car. That's a suggestion. I'm not giving you right or wrong there. Let's see if there's any further suggestions. Backwards. Next, we'll move forwards. Okay, so we've got some conflicting ideas, forwards or backwards. Okay, let's think about the girl herself, the girl holding the balloon. The girl, the child holding the balloon. As the car decelerates, what is their body likely to do in relation to the car? So as car decelerates, force on the solid objects in the car is going to be pushed forwards. So you'd expect things generally will move forwards as the car decelerates, as it brakes. That's what we're experiencing. We know that we experience a force against the seat belts if we're braking suddenly, and any objects that are loose in the car will move forwards. This is a helium balloon, so we also have to consider the car is full of air. Now, the air molecules are generally heavier than the helium molecules, and the air in the car is also going to be pushed forwards. The helium, being a lighter, less dense gas, is going to follow the density gradient. Now, the density gradient is going to go from a large density now as the air molecules are being pushed forwards to lower density at the back. The reason why helium balloons float upwards is because they follow the density gradient. They follow they seek the less dense air that exists at higher altitudes. Now in the car, we're suddenly putting that in the horizontal plane, and our density gradient is dense at the front and less dense at the back. So those of you who said the balloon is going to move backwards have got it right in this instance. The helium balloon is going to move in the opposite way that we might expect. These examples that I've given you are really just a couple of examples that we get through applying physical and mathematical concepts to what we might seem common ideas, and it's really thinking through the process in a logical and consistent manner, and that's what the physics course offers. And if I do see you in September, I'll be extremely excited to start a new course of physics with you willing and open to challenge your pre-concepts and actually think, well, what do some parts of my knowledge, how do they contradict other parts of my knowledge, and can I apply the rules of physics in order to come with a sensible suggestion for how the universe behaves the way it does. Okay, we're out of time there. I'm going to forward quickly to the transition part again. So if you didn't get the chance to see it earlier, there's some other questions here that you might want to have a go at thinking about as well. All of this presentation is on the files attached to this team. Thank you for attending. I will take a register. I'll do that. Other than that, I'm just going to take this opportunity to wish you a very happy summer holiday and enjoy your moment of freedom before it all starts again come September. Okay. Right, any questions that you want to put in the chat box? I'll have a quick look now. Take care and look forward to seeing you soon.